We get going. I'm Keith Summers from Productivity Quality. We're going to talk a little bit about CT measurement today. And Adam Clark is our Director of Metrology guy, so he's going to make sure that the stuff that we see is actually right. And Jim Nagy is our Principal CT Engineer. And so Adam's other job is to go next. And so in our lab, AIS, we've been using CT data for probably over 10 years. And for probably the first 4 of those, we did not have a CT machine, but we had all kinds of different data analysis tools. So we would send the parts out to some kind of a service bureau. They would do the CT scans, send the data into us. We'd do the analysis, and everything was fine. Over time, we found an opportunity to have our own CT system come in, and now we've got 2. So we'll kind of talk a little bit about our process and how we turn these CT scans into usable measured data. I don't know how many people are familiar with industrial CT at all, ran across other things. Computed tomography, and tomography is some Greek word that goes back to the Greeks, I guess. But it's simply seeing things as slices. Our eyeballs kind of give us something like this. Tomography gives us slices, and sometimes those slices are bing, 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 bing. But in our case, we're going to put something on a rotary table and take a bunch of slices, and maybe I'm going to say, well, I got 360 degrees. I'm going to take a slice every quarter of a degree, so now all of a sudden I've got 1,500 separate 2D images that I'm going to reconstruct into a 3D point cloud. And so the real advancement in computed tomography came when having to deal with all of these individual pictures. Even when we were at first just sending our data out, I sat down and visited with a guy who was doing the data analysis for us. And he'd say, okay, I've got all the scans done now. I'll have the data in the morning, because it would take 18 hours to reconstruct all of the scans into a 3D whole. And so as computing power has grown, all of a sudden computed tomography becomes a much more viable kind of thing. It takes a certain amount of time to do all these individual scans, but maybe only a similar amount of time to reconstruct them now. So the computed end of tomography is where it's really changed and made it practical for industrial applications. Yeah, I think you got to click it twice there because to make the video play. There you go. Volume Graphics is probably the main software provider for everybody's CT systems. So they got a quick video just showing I've got a source, a manipulator, and a detector. And in a real-time basis, we're taking picture, one after another, until maybe we have 1,400 or 1,500 pictures. Now I have to take all of those individual 2D pictures and construct them into a 3D whole. So this is maybe an STL file. So it is just a file of points turned into triangles. And from there, I can get some simple measurement data. But we'll see that the real power comes in when I bring in CAD data. So now I can bring my CAD data in, and now I can do a cloud to CAD comparison and get a pretty good idea in a color map or individual measurements of how I'm doing. CT has always been used for other more unique things, like simple wall thicknesses. And so I can put in a nominal wall thickness and I can quickly do all the analysis for that. And because I'm getting the inside, outside, and everything in between, I can also look for defects. So here's things like voids and porosity, and here's something in our native German that says, here's our defect information. But it gives us a way to slice and dice 2D and 3D fashion and look for different kinds of defects, voids, porosity, inclusions, things like that. And a really nice way to visualize things. And the ability to spin it all around, look at it in great detail, and do an analysis, spit this out all in individual images, but also real data. How many of this size void do I have? Am I over a threshold on a certain kind of porosity? And so that is the very basics of computed tomography. And the other advancement is as the sources and the detectors have advanced, all of a sudden the resolution gets a lot greater. You know, we sold some simple 2D real-time X-ray systems back when I started in the early 90s, and it was sold to casting companies looking for voids, looking for porosity. They weren't necessarily measuring anything simply because the resolution wasn't up to the kind of tolerances that they would encounter. But now all of a sudden, with greater resolution on our detectors, more power in our sources, we can all of a sudden get down to metrology kind of data that we need to spit out numbers that really have meaning. And so when you think about it, you know, we tell people every surface, internal and external, complete coverage, millions of points, all in only a few minutes. What's the catch? Why don't we do this for everything? And it's valid metrology. You know, I got to have confidence in these numbers. So I've got a CMM, and beep, 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 beep. It's calibrated by somebody with traceable artifacts. I really have confidence in the number that my CMM puts out. I have confidence in the number that my vision system points out because there's lots of traceability there. CT is a little bit newer, and they're starting to go that way, but mostly it's a lot of questions about, are you sure? You know, and if the tolerances are wide open, I'll say, yeah, I'm sure, this is not a problem. But as the tolerances get smaller and smaller, then you're, well, maybe I'm sure. I think I'm sure. I'm not certain. And so we'll talk a little bit about that. And so everybody in metrology has seen this for a while, but you know, we're concerned with both accuracy and repeatability. And in some of the things that Adam has found is that we will find sometimes CT results to be repeatable as we could possibly hope for. But an issue with accuracy. We'll say, okay, boy, I've got really nice CT results. They are all lumped together. Now I do my CMM results, and they're even better lumped together. Uh-oh, wait a minute. There's a big shift. There's a bias in accuracy. And so that's something that we put a lot of time trying to think about and make sure that we have accurate and repeatable data. And how do you get to accurate and repeatable data? Standards and standardization. You know, standards, physical artifacts. We've got countless artifacts for all the different machines. For CMMs, we've got step gauges and gauge blocks, COBA bars on vision stuff. We have different kinds of glass grids, and so hundreds of thousands of dollars in artifacts. And how do we use those artifacts? Well, we need to have some standardization, have some standard procedures. In most cases, we don't cook these up ourselves. When we ever cook them up ourselves, we always seem to make mistakes and we look stupid. And so, fortunately, ISO, ASME, sometimes our manufacturers give us standard to say, okay, take this artifact, here's how you use it. And that's how we kind of go to work on all our CMMs and vision systems. Put those two things together and we can feel pretty good about our results. Now the last little thing here is when you think about it, go to the next one maybe, this is a real practical standard, been around for quite a while. If you've got a CMM, somebody comes in and they may have a gauge block stack or some kind of a step gauge. You know, they take the probe and they go beep, beep, beep all along the way. And then all of a sudden they say, hey, it's in spec, it's good. Great, I'm going to go to work. And now all of a sudden you look at your parts. A polished machined ground surface, a polished machined or ground surface. If my CMM is repeatable and I've got an accuracy number for my CMM, and now I'm measuring my parts and they look just like what my artifact looks like, that's a pretty good deal. So if I say my CMM is accurate to 2/10,000ths of an inch when I measure those gauge blocks, I can probably feel pretty good. I'm good to 2/10,000ths of an inch when I start measuring my parts. And that's been the beauty of this ISO 10360-2 standard. And you can never get too much of a good thing. And so a little bit later, somebody says, hey, that standard's been great for CMMs. Let's use it for our vision systems. And so he said, well, okay, well, let's see, what do we do on the CMM standard? Well, I've got like a step gauge, and I got like 25 steps along the way. How do we do that on a vision system? Well, okay, I got it. Let's get a chrome-on glass linear scale, and we'll use that in that same fashion. I'll look like parallel to X, parallel to Y, some diagonal stuff going around. And I'm going to have almost that same standard, but and apply it to my vision system. Good idea. Problem comes in, how many people here make chrome-on glass parts? Not many hands go up. Every so often some hand will go up, well, I make chrome-on glass parts. But that's where this starts to get a little more fuzzy. So when we calibrate a vision system, we give a number and say, hey, it's good to 1/10, 50 millionths of an inch based on how well we measured our chrome-on glass artifact. And if somebody says, hey, that's great, I'm going to measure my plastic injection molded parts to 1/10, 50 millionths of an inch. Well, not so much, because the edges on that molded part are a lot different than that chrome-on glass part. So this is a good standard, but because of subjective things in a vision system, magnification, edge finding, lighting, all these kinds of things add up to make things a little more subjective and a little harder to say, hey, it's good for 1/10 on my CMM, maybe not so much on a vision system. Well, and so you can never get too much of a good thing again. And so there is a newly released CT standard from ASME. And it has artifacts and it has procedures, but the difficulty that comes in here now is that the subjectivity hits another level yet. So, gee, my vision system, well, what about magnification? What about lighting? What about edge finding? With CT, take it up a notch. It's a big notch, and all of a sudden I've got my power, I've got my number of steps, I've got the resolution, I've got all these different subjective decisions I've got to make before data gets spit out. So that makes CT a little more challenging, and that's why we won't just say, oh, just measure with CT, because it'll be perfect all the time. And so this is a little bit about our process to get there. And Adam has been working on a project for a customer on a lot of CT stuff. He's had the chance to travel to beautiful Indiana for 10 weeks since February. And very smart medical products company. And they said, okay, here's what we got. And they were very good. CAD data, everything was designed in SolidWorks with model-based definition. So all the tolerances are embedded in their CAD data. They say, here's the parts, here's what I need, help me get there. And they had a CT system on site. So we say, okay, that's great, that's what you're going to give us, here's what we've got to give you. What a proven measurement capability. We can't just say, oh, here's the spec on this machine, have confidence. We had to give them hard, verifiable numbers of how much confidence they could have in our measurements. Mostly they were looking for first article data. I've got 32 features. I need pass-fail on those 32 features. But also, they have certain process control requirements, looking at certain key features so they could better steer their process. And at the end, they wanted to make sure that the data was secure, stored, searchable. So that was kind of the goal of our process. And so what we came up with was a big flow chart. Being measurement nerds, and we're not going to go through the flow chart, but we sat down and talked a lot about it and say, how do we make sure? How do we know that these numbers are right? And that's something that we try to do a lot in AIS is the question, how do you know? If somebody's running a CMM, is this going to pass? Is this capable? Is it a capable gauge for this application? Oh, yeah. How do you know? Oh, they say, well, okay, here's my calibration data, here's the artifacts they use. They can actually explain why people can have confidence in the results. So we came up with this big flow chart that we won't go all the way through, but it represents our thinking about how do you know. Okay. And so our how do you know goes back to some other kind of measurement system. And so in this case, I don't know if people deal with these at all, it's a lure fitting. And this is a great application for CT because it's lots of small internal features that you can't really get any other way. So you can't CMM these things, but what you can do is that we can find a certain number of features that can both be measured with the CMM and measured with the CT system. So let's look at those common features and see how the CMM and the CT kind of correlate to one another. And that's because in this case, we've got a really nice high accuracy CMM across the street that happy to give anybody a tour if they'd like to see it. And that spits out numbers that are really low uncertainty. We've got lots and lots of confidence in these numbers. And so that's one of the first things we do is we just go out and get a point cloud of the features that we can get. So we look at the print, we look at the CAD model and say, hey, we can measure that ID cylinder. We can measure that OD cone. We can go down that next ID cylinder. We can get the outside. We can get a step here and a step there. And so we get a cloud of points that we've got a lot of confidence in, and that becomes our reference to compare back to the CT data. Thanks. And then Jim has to do his part, and he'll give us in a little greater detail. But we're going to put the part now on the CT system. And we're going to get a bunch of our 2D images. We're going to reconstruct them into a 3D image, and that 3D image is going to have millions of points. Well, more than 1 million and less than 10 million, but lots and lots of points. And if anybody has dealt with these scanning systems, that's as much bad as it is good. Because when you measure with your CMM, in essence, you own every point. So if I measure a bore on my CMM with 17 points, I cheerfully own 17 points. If one point is screwing me up, I can come back and deal with that point. If I own 10 million points, that's a lot of ownership. Now, where's the bad data? I don't know. I can't even go back and replicate it with a CMM. I can say, hey, go back and retake that point. With CT, I just got millions of points. So we have to have some way to manage these points and reduce them in an intelligent fashion. And so that is in our process, and Adam will talk a little about that. But here's what we would come up with at that first validate the process sort of step. And so in one hand, I've got this very nice, neat, ordered, beep, 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 kind of CMM points. So I really understand that. I feel good about it. I have confidence in those answers. And I've got millions of points, I've reduced a little bit, to give me the corresponding CT answers. And then I can say, okay, well, how do they compare to one another? And so in this case, we had lots of profiles that we were going to look at. So on the left, on the infinity side, there is my CMM data that I feel really good about. And there's my CT data that I'm not so sure about. Well, what's the difference between those two? And as we look at this in metric units, I'm saying, oh, that's not too bad. 11 microns, 1.4, 3.1, 1.4, 8.4, 6.8, 2.7. I can live with that. And those are some pretty good numbers from my CT, the delta from my CMM to my CT. So I'm going to declare victory and feel pretty good about things. Well, again, I'm going to make some inferences later about the underside of this thread form here that I can't get at with the CMM. So I just have to say, okay, I picked all the features that I could find that are common, and I'm seeing what my results look like. And I say, I feel pretty good about that. I'm okay to go. We did this demo for one customer on their parts, and it was looking kind of lazy, but there was one that was 25 microns, about 1,000th of an inch. And, I told the customer, this was just a first blush at it. There's other things we can do. We can take more data. We can change settings. I'm sure we could optimize that. Well, this guy said, hey, it's a plus or minus 10 thousandths tolerance, and you're telling me you can do this CT to 1,000? Don't bother going any farther. This is fine by me. And so that's what we've kind of seen, is that this kind of sets the threshold of confidence about how well we can do with the CT data. And so in our case, and we'll let Adam and Jim do a little more explanation, this particular customer, not the part shown here, is that they said, okay, we use SolidWorks, and everything within our model has all the tolerances embedded in it. And so we use a package called Smart Profile, and there's a new interchange format called QIF, the Quality Information Format, and SolidWorks in its case has got an export. You know, I want to export as, and QIF is one of the choices, and so it exports the model and all of the GD&T appended to it. So when we start in Smart Profile, we're pretty far down the track. And kind of the beauty of that, and we've always kind of seen this, is that the designers think one thing, and now the QA guy has to look at that design and say, I think this is what he means. Yeah, that's probably what he means. This enables us to take the designer stuff, no judgment, no translation, and get it right into the model and come to the answer. So that's the beauty of this MDF. And Adam can just do a quick demonstration of how we go about that.
Sure. So we've already created a CAD model, a QIF, with this definitions defined in it. So I'll just show you a quick import via Smart Profile. So this is as if it came directly out of SolidWorks, which it did, Jim did for us. And then we'll bring it right into Smart Profile, and you'll see that it already basically defines the entire project for us. So in our Smart Profile here, we have options to import CAD, import points, or import PMI, product manufacturing information. One of those formats is QIF. So we can import that here. 1 second. Trustfully on my flash drive in my pocket. And here we have a QIF model. So we can import that. It already has the units defined in the model, and it already has all of our surfaces defined in Smart Profile. So we can see it brought in colored surfaces from our CAD defined in SolidWorks, along with all of those profiles. So,
and one kind of the neat thing about a scanning device, you'd think if I brought this into my CMM, as Jeff would know, doing lots of PCDMIS programming, well, what about probe qualification? What about positioning? What about fixturing? What about all those CMM kinds of things I'm going to have to do before I can just go say, go measure that? With a scan is kind of cool because I just got a bunch of points. Got to make sense of all those points, but all those other CMM-like overhead things of probe qualification, probe position, fixturing kind of goes away. So all of a sudden we get right from QIF right into answers.
Yes. Our CT is not going to result in a lack of points on any surface that we're interested in measuring. We're going to have thousands of points on every single surface within this model. So that's just a quick overview on bringing QIF into Smart Profile and how simple it can be then to move on to our analysis. Next is Jim.
Okay. So one thing we would do there, and we'll kind of get to this a little later, is that we brought in like the full first article. So there is all 32 features. And from there, maybe you want to pare it down because these Smart Profile projects, and say, okay, what can I measure with the CMM and with the CT? And so, okay, I got 32 in my first article, but there's only 8 features that I can get CT and CMM data, so we just strip it out. Quickly pare it down to what I want, or for some reason, if I don't have all the features I need, it's very easy in Smart Profile. Say, hey, I forgot about this profile, I forgot about this perpendicularity, and we can add in whatever features that we want. So now we've got a couple of Smart Profile projects. One of them is for our proof of concept, and the other is our full first article. And Jim, this is kind of what we've got.
CT in a little bit more detail, how it works. So, let me see here, pointer. So we have CT scanner, and next to that, or embedded in the CT scanner, we have the acquisition PC. And
I could be the Vanna White kind of
we have,
can't jump high enough.
Right here, we have the Reconstruction PC. So the CT scanner basically rotates the part around. The acquisition PC gathers all of those images that Keith was talking about, And then the Reconstruction PC basically takes all of those images and brings it back into a three-dimensional object. So we look at the system components. Basically, we have the source, which is the X-ray tube. And then we have the detector. That is what gathers all of the images from here to there. We have the manipulator. That is the XYZ stage with the rotation. So we have the XYZ movement. And then we also have the rotation. So this is the sample part. And that part rotates around while it's scanning.
And you can imagine that it is kind of like an optical comparator. You know, here's my light source, here's my part, over here's the screen. And so the closer the part gets to my light sources, the more I'm blowing it up, kind of the better the resolution I'm going to see.
Exactly. Okay, so next screen. Here is the system settings. So up in this window, we have all of these little settings for each one of our things that are important, basically. We have our tube settings, which is the source tube setting. We have power and the amp setting. So the thicker the part, the more power we need to get through that part. So it's X-ray. If you've ever had, hopefully not, a broken bone, you go to the doctor and they do an X-ray and they can see through your flesh, basically, and detect a crack in your bone, basically. This is exactly the same way it works, except for we're taking thousands of images. So we set up this power settings for the tube, and then we have the imager or the detector settings over here. So we have the frame rate and the averaging settings for the imager, and then over here is the tomography settings. This is where we determine how many slices we want that, or how many images we want that tube or the system to take as it's scanning. So
one thing that's kind of neat about this particular part, and Jim's got some samples over by the machines, it has two different materials in it. There's kind of a hard plastic outer and then a softer plastic inner, which is more of a silicon rubber almost.
I believe it's polycarbonate and some silicone inside. Yeah.
And so they have different densities. And so in a CT system, it's all about density, so it's really easy sometimes to be able to separate one material from another. And the other thing that's kind of cool then for something like assembly, I want to see how this thing looks like on the inside. Well, every density has its own footprint, kind of, and we can really separate, show me this part, how it lies within the other part.
Yeah, and we do have a scan of this part over in our area, in the CT area, with all of sorts of different results. We can do porosity, we can do assembly, we can do dimensional analysis, and we have all of that over there, so you guys can come by afterwards and look at that. Okay? Okay, so basically, if you look here, it's rotating around and it's gathering all of the images here. Go back and kind of replay that. Kind of went by fast. So it's rotating around. Here's like a zoomed in view of the part. And then here's the TIFF images. It's gathering many more images than this, but this is kind of a real good example of what it's gathering before it does the reconstruction.
And here, again, on this whole density thing, it is just sitting in a foam block that's incredibly not dense. And so that just kind of washes away. So we can put it in some kind of soft material. We got like the stuff that you pot your plants in, or just pink styrofoam or other kinds of foam. And we can embed, we can make a fixture, put the part in the fixture, and the fixture just goes away when we actually do the CT image.
Yeah, what Keith is talking about right here. Here's the part and the sitting on foam, but the images, you cannot see the foam in the actually scanned images. Okay, so the reconstruction part of it. Basically, once all of those images are gathered, we have this separate exact software. Basically, the images come into this version of the software. We load them, and then we switch over to the Reconstruction. There's all sorts of other tabs that we can do to get rid of scanning artifacts. If you're scanning metal, you have beam hardening artifacts and metal artifacts that create streaking that we can get rid of with these different tabs. But for plastic, basically, you don't really have to do that. So, okay, so once we've done the Reconstruction, we have our 2D tomographic images that get reconstructed, and then we also have a 3D image over here. And then after that, we export to a software called Volume Graphics. That video that Keith showed earlier was Volume Graphics, and that's the software that does all the porosity analysis, the dimensional analysis. You can export CAD models as step files or STL files to be used basically any way that you want.
And Volume Graphics is kind of the Swiss Army knife of softwares where it does everything. It does all of the material defect analysis. It can do all of those assembly kinds of things. It can do some of the metrology kinds of things. So if you want a one-stop shop for all of that, Volume Graphics is kind of where you're going to go. If you say, no, I'm measuring parts and I'm fanatical about measuring parts, that's why we skew to Smart Profile, because from a GD&T standpoint, there's a lot of different ways to slice and dice things, and Smart Profile probably does the best job of conforming to the GD&T standards, but also it's smarts about turning the 1.5 million parts point into usable points.
Okay. So once we have all of that done, we basically, for going to what Adam is talking about, we would export what's called an STL file, which is basically a point cloud, and that gets imported into Smart Profile.
Yes.
All right, so we'll walk through the final steps of our Smart Profile analysis here. So part of what we're doing in Smart Profile is we're comparing our CT scans to our CMM scans. So we step through a subset of the total number of features on this part. We see the 4 surfaces here that we were able to measure well on our CMM. That resulted in 114 total points across those 4 different surfaces. So significant reduction in points, but again, we have very high confidence in these points. What we need to do then with our CMM data is sample the equivalent points on the surface in the same area as our CMM. So we can do this within Smart Profile. So we'll go from our 1.3 million points that came out of our SEL and our CT scan and sample that down to the same 114 points that we did out of our CMM. One step further in that is we add some additional, and they're highlighted in gray as redundant callouts, but we're adding additional callouts to profiles that we're looking at to isolate size and form characteristics. So we don't want to look at just the total profile value. We want to separate that down into further components so we can see if we're just getting more noise out of our CT scan, if we have a size shift in our CT scan. So the CT scan we saw the panel detector. That's just a panel detector like you have in a video CMM, right? It's just a 2D array of pixels. So we can compensate the size of those pixels at different magnifications. So we might have a size bias that we need to correct going forward in our CT. So over here on the right, or I guess left when you're looking at it, we have our blue points. So we're isolating size and form characteristics. So our center dots there are our average size of 2 features of interest that we see over here on the right. And then the whiskers on the plot are the form. So what the goal here would be is that our CT data lies within our CMM results. So on the furthest left image, we can see we have almost the exact same size value. So we're happy with the size of our pixels. And we have comparable form values. That's more or less what we expect to see. On the right side of that plot, we can see we have our 3 blue dots all basically in a line, so we have high repeatability on our size there, but that size is shifted about 5 micrometers above our CT data. So this is all from the same scan, but some of those are looking at internal diameters versus external diameters. So as we transfer between different edges within our part, we can see different results in our CT scans. So this is a bias where we might say 5 micrometers is not a concern for me, or maybe this is another bias here where I have to go and correct my size data coming out of my CT. And this is all going to be part dependent, material dependent, and so to really have high accuracy CT results, this is something you have to break down on a part by part basis. Next, I'll step through this live afterwards, where we're going to bring in our total CT point cloud into Smart Profile. And if we were doing our first article inspection, we don't want to analyze 1.3 million points. It's going to take a long, long time to do, and it's a little redundant. So within Smart Profile, we have ways to intelligently reduce our point cloud to bring it down to more of a manageable size. And a manageable size is typically like 10,000 to 50,000 points. So still significantly more than we would ever see out of a CMM, but much easier to evaluate than 1.3 million points.
And any GD&T call out, especially like profile, the one outlying point drives the answer. So all of a sudden, if I've got 1.5 million points and there's a certain amount of noise in there, if I use all 1.5 million points, that one little outlier is going to give me my answer, and I'm not going to be too happy with that answer. And I also probably shouldn't have a lot of confidence in the answer because I know there's a certain amount of noise within the CT scan. So intelligently reducing that down is how I'm going to get to values that I can have confidence in.
Yeah, so as we step through this, we'll see in Smart Profile we have a function called CMM-like sampler. The goal of this function originally was to do that CMM to CT comparison that we saw earlier, where we want to compare identical points between our CT scan and our CMM scan. And we can do that by importing our points, our sample locations from our CT. A side function from that we were able to get. So let me load a sample here. So we have what would be our full first article inspection on this lure. I already have a point cloud here that I brought in and sampled down, but we will bring in a new point cloud. So we import some points. Okay, we'll start with the leading points. So part one, run one. So obviously we want to look at repeatability. So we're going to theoretically we'd be stepping through this multiple times here. So we can bring in our points of whatever unit they might be. We know that the points here are the same as our project file. As our point cloud comes in, we'll see it as green points somewhere in 3D space. So part of CT is our coordinate system is looser than if we were to measure on a vision system or a CMM system. So often our points are isolated somewhere in 3D space that it's hard to bring in consistently aligned originally. So we can see what appears to be a second solid CAD model, but this is actually our point cloud of lots and lots of points. So if I zoom in, we actually have discrete points there. We can set up a process chain to bring in these points. So this will align our points to our CAD, confirm that alignment. We can force our alignment to some specific features or features of interest. So here our threads are a mating feature. So we're going to focus our alignment on our threads for this. And then I can show you the window afterwards, but we apply this CMM-like sampler. And so for each individual surface on my CAD model, I can define how I want to sample points on that surface. So I can target specific areas and specific sizes to average my CT points and sample that down into a single point afterwards. So you can see on our first step there in our process chain, we had 1.3 million points, and our CMM sampler here will result in more or less 10,000 points. We'll step into it once it's complete. all of this is an automated process that we introduced into our CT scanning. So as soon as we set this up once and we're running repetitive parts, this is never something we visually see again. It's just going to happen in the background. So we can see we sampled 9,600 points, and I have this option to configure my sampling. And so this could be a general global sampling. So I can sample uniformly across my entire CAD surface, but rarely is that really what I want to do. I want to focus in on my tight tolerance areas and sample less points on my looser tolerance areas. So these surfaces in green are specific surfaces that I've stepped into and set up different sampling techniques. We can see all of these individual points with some radius around them, where we're going to average our CT data in that space. So I have control over those points to say I really want to increase my sampling radius, and I get larger averaging circles, basically. So I can step out of that and confirm I have a total of 9,600 points at the end here that I will bring in for my analysis. We can run.
You're done?
That's it for me.
And so again, that's the, so you're doing the analyze. And so now it's running. And again, for this customer, it was all in one big macro. And so they would have a CT operator that would load the part in the CT, hit go, and then go do what they're going to do. And at the end of the CT scan, it does the reconstruction. The data, Spark profile sitting off the side saying, where's the data, where's the data, where's the data? Data shows up, it grabs it, it does everything that Adam just showed you, and then out the other end it spits out whatever report we want. Could be pictures, or it could just be all the numbers going into some kind of a database or some kind of an inspection report. So once it gets set up, the complexity kind of goes away. You hit go, and the answers come out the other end.
Yes, their final solution, they wanted printed reports for every single part that they scanned. So after all of this automation, the last step in it was the printer finally printed the report, and that's what the quality guy looked at the end. But there was no human interaction after the first inspector put the part in the CT system. The next step in the process was the final quality guy looking at the printed report.
And that's kind of the extreme end of things for customers who have dedicated into their process in our lab. And we invite everybody, if you're curious, come on down. The two systems are down there running. And we are inspecting parts every single day. And we don't do the automation end of it, but this is the process that we follow. And if the tolerances are wide open, we know the basic capability of the CT system, saying, okay, I don't need to go off and do all these CMM comparison features. But all of a sudden, as the tolerances get tighter, now we will tell the customer, you know, if you really want to have confidence in this data, here's the process that we should follow. We believe for this feature, and this feature, we are going to put it on the CMM, we're going to get some data, we're going to put it on the CT, get some data, do a comparison, report back to you and say, here's where we think we are. And they'll hopefully say, yes, that looks good. Then we'll do the rest of the analysis. And for us, in most cases, it's smaller runs of parts, and so we are more manually loading them in, getting the data, doing our analysis, and sending the results back. And for us, you know, this is kind of the bread and butter of things. If you say, what part do you inspect more than anything else? It's lure fittings. And lure fittings, I'll be ran across them, they're an ISO standard. So from a syringe to a needle, it's a lure fitting. From your IV bag to the tube, it's a lure fitting. And so they all have a common ISO stuff on the inside and then the customer design stuff on the outside. But that is an interchangeability kind of thing. Gee, if one guy makes the bag and another guy makes the tube, are they going to fit together? And the lure standard and ISO standard guides you to that. And of course, that is kind of traditional plus or minus tolerancing, which some people here who've been through a lot of GD&T training go, no plus or minus tolerancing. And so we do that answer, but then we also do the profile answer, because the profile answer really gets at, will this thing work? And working here is not leaking. So that's basically our process, and these guys will all be down right by the CT machines, kind of in the back of the PQI area. We're more than happy to give you a demo of it, and this is what we do on a day in, day out basis, so we're always happy to have customers come in at any time, bring in your sample parts, and we'll show you what we can do. There you go. Thank you very much. Oh, I think there is a short survey that if you could fill it out and make us look good, it would be greatly appreciated. So we look better than that last guy who did his tooling demo.
Yes. Oh, so what kind of power do you have on your tubes? Meaning, can you look through 1/2-inch aluminum or 2-inch thick steel? Or I'm a steel guy, so I had 1 3/8 diameter steel bars. I wanted to look for cracks.
1 3/8.
Yeah.
That's a lot. That's pretty.